Welcome to Windows Azure from the pulpit to the whiteboard. My name is Ryan Dunn. I'm joined today by Wade Wagner. You'll see him sitting over in the corner. Before we get started, I just kind of want to do a little level set here. Most of this talk is going to be on lessons learned or principles that we've found in building real-world applications in Windows Azure. As a background, you have to understand that Wade and myself both came from Microsoft. I was one of the first Windows Azure technical evangelists. Wade was as well. We did things like the cloud cover show. We used to build the training kits. If you saw Mark Rusinovich's keynotes, we were the people behind the scenes actually setting those up and doing those kinds of things. So I've been working with Windows Azure for a very long time. In fact, since once it was called Red Dog, before it was even released. Then we decided to go out and actually join another company. In one case, a startup. In another, we're with Aditi, a company today that's a service integrator. And we build these services using the platform that we've been evangelizing for the last, 7 years? Something like that, right? And there's a lot of valuable lessons that came out of this. So some of the scenarios we're going to be talking about are things that actually have happened to us. And we're going to try to, whenever possible, put it into the context of a story and let you know what we figured out. And we'll try to generalize it so it's applicable to you. But to do that, we're going to have to explain a little bit about what we built so it makes some sense in your mind as we do this. But before I get started, how many people are here from Spain? There's no one. Unbelievable. I was going to say, we got a chance the previous 2 days to walk around this city. It is fantastic. We literally walked 20 miles, which is, it's like 500 kilometers or something, right? It was awesome. It was a really beautiful city. We met some really nice Spanish folks. They taught me some Spanish, so I'm going to try it out with you guys. Hola. Buenos dias. Tengo un mapache en mis pantalones. Okay, we'll work on that. Here we go. So again, we're going to talk about lessons that we learned the hard way. A lot of this talk is going to be focused on how we built for scale in Windows Azure, some of the traps that we fell into. We're going to talk a bit about automation and testing, how we run our operations at Aditi, and how we've been able to be very successful this way. We'll talk a little bit about our deployment patterns and some thoughts that you can take when you go to deploy in Windows Azure. And finally, we'll wrap up with a quick discussion on handling disaster recovery and downtime. It's going to happen, and you just need to think about where your single points of failure are in your system. All right, this is I promise, our only marketing slide. So we come from Aditi, as I said, and we work with really big customers. And most of our work is focused these days in the cloud and in Windows Azure in particular. And with our background, we hope you trust us when we say we do a lot with the platform. We know it pretty well inside and out. All right. So one of the first services I was involved with and built was something called AzureOps.com. Now, AzureOps.com actually was a monitoring service. We monitored at our peak a few thousand VMs, and we were aggregating and analyzing and indexing trace data and performance counters. We had an auto-scaling engine on the back of it, so you could specify, if my CPU is more than whatever, 60% for 10 minutes, go ahead and auto-scale me, and then wait 20 minutes and scale me down, or keep going and scale me up if it continues. This kind of behavior. You'll note that, yesterday or the day before, the platform now has auto-scale in it. Well, we did this 2 years ago, something like that. So we had to build this massively scalable infrastructure, and we had to do it all, and it ran on 2 smalls, 4 mediums, 2 mediums per data center that we were co-located in, and 12 extra small instances. And I'll kind of get to why we ended up with that architecture, because that's not where we started, actually. Secondly, we've just released a service in the store called Scheduler. The reason I bring this up now is because the architecture we're talking about here is going to be very related to what we built for our Azure Ops. What this does is allows you to do simple time-based jobs, so cron jobs. You can kick these off. It'll do a webhook. It'll push something into a queue for you. You can alert yourself every hour, right? Time to back up, time to clear your cache, that kind of behavior. This infrastructure is meant to be highly scalable as well, so we want to serve thousands and thousands of tenants simultaneously. And we want to do it with as little infrastructure cost to us as possible. So, quickly, here is the architecture that we've been talking about here. We use something called CQRS. This is our chosen architecture. I'm not going to get into a ton of details about CQRS, but if you would have a chance, I'd really recommend investigating it or some of the sessions earlier in the week here. But what we have at the top of it here is we have a service client. The service client simply knows how to push messages into a queue. This queue is really serviced around an event bus. That event bus then dispatches those messages to our command handlers. Our command handlers work in conjunction with our domain model. So you can imagine something like user registers. The user sends a command that says register user. We handle it here in the command handlers. And eventually we say user was registered. And we emit an event. We store it. And then that event gets popped back out to our event bus where we have denormalizers there that will actually write the data that we want into a separate view storage, and then that will be returned to the customer back up through a query interface, a very light query service on top of it, if it's tabled storage, or if it's a JSON file that we're serving, we'll actually serve it just basically directly straight from storage. And it turns out this right here is going to give you extreme scale on your website. Right? We're effectively doing nothing. We're serving a static file. We're serving static content at the end of the day. But because this entire process back here is asynchronous, there's different challenges and different opportunities we have. So we can scale this independently. We can work independently. Few of the reasons we chose this. Again, our back end, we keep it async. We can actually scale this independently. We can push all of our work to our back end. Our command handlers and event handlers actually become relatively isolated in this model. There's not a lot of dependencies between them because the events are being dispatched directly to these. Makes it easy to test. When you have a small team and you don't want to be stomping on each other's code, this actually works out really well. We use event sourcing. Event sourcing was the little box where was orange. What that does is we record every action that occurs in the system. So if you register with us, we have an event that says tenant registered. If you set up a scheduled task with us, we scheduled task created, scheduled tasks updated, so on and so forth. What this does is it gives us an audit history. We know exactly why the state of your scheduled task is in its current state because we can look at the events and rebuild what we call an aggregate of the state of your scheduled task or the state of your tenant. When somebody comes to us and says, I don't know why this isn't working, my data is not showing, we can go through and we can say, well, look, on this date at this time, you actually told us to go delete this field, something to that effect. And then because we're recording the events as they occur and we have this event log, we can actually change and modify all the views in our system. And it allows us to replay those events and rebuild the views as if they'd existed for all time. This is a very powerful feature. Now, back to our scenario. So we were monitoring a customer, a particularly large one. They were running 300 VMs plus, with hundreds of SQL Azure databases. They had an error in their DB connection logic. And in an extremely tight loop, all 300 instances were tracing the error with a full stack trace. Now remember, we're going to index this data. Turns out they were generating more than 2 gigabytes per minute. So 10 gigabytes in a 5-minute range of data. We had 16 instances at one point trying to pull this data to index it. We completely saturated the NIC on the box. And we're looking at it and going, what are we going to do here? This is crazy. One tenant has completely consumed all of our services in a multi-tenant environment. Our autoscale actually noticed that things were starting to back up. So our autoscale being helpful, decided to throw more instances at it. And then the way our system works is when a message comes in and you don't process it in time, it reappears, right? You know what Windows Azure queues? Message goes in. If you don't process it in invisibility timeout, it reappears. So we couldn't process the data fast enough. The message would reappear. Another instance would pick it up and start all over again. So now we have like 32 instances trying to index the same data. It was a complete mess. This is what we learned. From the very beginning, plan to throttle. Throttle, throttle, throttle. What we did was actually we rewrote our aggregator. We said, look, we're going to pull the first 50,000 events in the 5 minutes, 50,000 traces. That's a lot of data, it turns out. If it's more than that, we're just going to throw a throttle there. The customer can come back to us and say, look, you didn't get all my data. We're not going to try to get it all. But we're going to tell them that, look, we can't do this. You're monopolizing all of our resources. That actually fixed the problem. What we found, though, is we had to be very, very cautious about our retry policies. Right? We had to increase that timeout significantly. We don't want that to occur again where another instance tries to jump in and help, and we end up monopolizing both of those instances. So this leads us to our first tenet, protect your service. Assume from the very beginning that the worst will happen. It will. Your users will absolutely find a way to screw you over. They will submit crappy data when you don't think it's possible. They will give you the worst input you can possibly imagine, and they will have the strangest layout that you never thought possible that could occur in Windows Azure or any other app development. And you have to plan for that. You have to plan to throttle from the beginning. Never assume that you can handle all the data that you're going to have. Plan from the very beginning. Whether it's timeout, I want this to finish within 15 seconds, 20 seconds, or the amount of data that you pull, the first 5,000 records. Be very, very wary of retries. Automatic retries sound great in theory. In practice, they don't work very well. We were bit severely by automatic retries in the Windows Azure Storage Client. How many of you guys use the Windows Azure Storage Client? A few of you? The Windows Azure Storage Client tries to do a very nice thing for you. If an error occurs, the automatic retry policy jumps in and it retries it up to 4 times, 30 seconds apart, right? So you got at least 2 minutes there. But it's pretty dumb. If it's a 404, it'll retry that 404 4 times. It's a 404. It doesn't exist. How is it going to exist the next time? Or a 503. It'll retry that. So you got to turn off all those automatic retry policies and be very explicit about the cases you want to fail. Fail quick. Get it done. Get it out of the way. If it's a real problem, put it into quarantine. Or if it's a retriable condition, retry it selectively on your own terms. Don't use the automatic retry. And learn from your mistakes. Our next scenario. Where our autoscale system would periodically kick up 4 new instances. The queues that it was based on, we were watching a queue, would bleed down, then they'd build right back up, and we'd scale back up. So if you saw our instance count, it was like 4, 2, 4, 2, 4, and it was just very cyclical. We had no idea why this was happening. So what we did was we decided to profile. We took custom performance counters and we started to actually profile the actual commands and the work that was being done. We found that our calls to the Service Management API were the culprit. So we would have on average about 60 seconds to determine your topology. So get hosted services, find out your storage accounts, so on and so forth. But some of them were running as long as 240 seconds. So what we did was we routed those commands to a separate queue, and we put 12 extra small workers on there. Now, at the time, this was the same cost as it was the same cost as 2 small workers, but we got 6 times the number of workers on those queues to handle these commands. We were just sitting there on I/O. We weren't doing anything really useful. So that's why, if you remember the slide in the beginning, I said that we had 12 extra small workers. That cost us the same as 2 small workers, yet we were able to process 12 times, 6 times as much work. Next, we would have a customer who would update their settings so they'd go change something on the website. Because we use a asynchronous process, that has to go get dispatched as a command. An event has to be raised, which gets handled by a denormalizer, which writes the view. Right? It's asynchronous. But the customer would be sitting there, kind of a little spinner, waiting for that command to get finally processed so the view would get updated. It's taking forever. Customers contacted support, said, what's going on? Turns out that we had some commands from customers that are being routed to the same queues as what some very long-running commands were. So we had them stacked on queues. We quickly determined that what we needed to do was create a UI command queue. So we needed to determine if that command was coming from a user and would have an impact on a view, if it was coming from our scheduled engine and was really just a back-end processing task. So we created essentially a VIP queue, put some dedicated resources on it, the problem went away. This leads us to our next tenet. Push all your hard work to queues. Go async. In the CQRS world, you're going to be doing this anyways. You're going to have an event bus, a dispatcher. It could be using RabbitMQ, ZeroMQ, Windows Azure queues, Service Bus queues. It doesn't really matter. You're going to be more than likely queuing up here. You want to prioritize those queues. Make sure you understand what has to be done first and what can kind of wait, what's low priority. Data aggregations for us turns out to be lower priority than things on the UI. At the end of the day, this alleviates your front end completely. Your front end just sends a command, it sits there and polls, and it returns views straight to you. I'll talk about read optimization in a little bit, tell you what I mean by this. But with this, your web servers are basically static file servers. And you get tremendous scale. Combined with eTag caching, they almost have to do nothing. Okay. This is real data, by the way. So this is one of our deployments, and we were monitoring it. This is about 10 hours, something like that. Yeah, about 8 hours, 10 hours, somewhere in there. This is our CPU usage. What's wrong with it? I don't see anything wrong with it. It looks fine. I don't know. It's bouncing around, but it's between 15 and 40%. Oh. So then we started to zoom out a little bit and found this was the range we were actually looking at. This is 10 days. Now what's wrong with it? Tell right away something's happening in our system that shouldn't be there. We actually found out that we had a serialization of event store issue. If you had a ton of events, the cost to load all those events up into memory and deserialize them actually got exponential on us. What it did was it pegged that CPU during the deserialization time. We fixed it with actually an implementation of snapshotting. So we'd snapshot the state of the events, a few thousand into it, so we didn't have to read those again. Which brings us to our next point. How do we know if it worked? You have to go back and look at the data. We know it worked. All right. So we had this queue length in North Europe. And it was consistently longer than North America, despite having fewer tenants there. So we had way more customers in the US at the time. We had like 5 customers in Europe or something like that. Our autoscaler kept aggressively scaling up our North Europe deployment to deal with this queue length. We couldn't figure it out. We're like, there shouldn't be that much work for this to occur. Remember, now we've instrumented too. So we actually could see how long it took us to for aggregations. And it was about the same time. We couldn't figure it out. It turns out that one North Europe tenant had used the same storage account for both load testing, their dev test, as their production environment. So imagine this, if you know how table storage works, they've generated terabytes of trace data into a storage account, but it's all for a deployment you don't care about. And then they have a production system using the same account, and they say, please look within this terabyte of data for my production data. It was literally trying to find a needle in a haystack. So we had to tune our timeouts pretty aggressively for this. And this was before we even got to the part where we aggregated. We had to figure out if there was data there to be aggregated. So that's why it didn't show up in our measurements. So our tenant here. You need to identify your bottlenecks in the system. Instrumentation is going to be key. If you can do custom performance counters, fantastic. They work really, really well. If not, even tracing within your system, hopefully in a central way, to give you an idea of how long a particular method lasts, works great. So in our message dispatcher, when we go to invoke our command handler, there's actually a trace that we have a timer that starts, and if it's more than 10 seconds, we actually trace a warning out. It says, look, this command took more than 10 seconds to process. You might want to be wary of what it's doing. You really got to look at data over time. It's not enough to look within a snapshot. That was the example you saw with the performance counters. You have to look at it over time because you're going to look inside a window, everything looks great. Look at it over time and it looks terrible. Profile your code, but be sparing on this. Profile your code when you think you have a problem. Not always hook up a profiler, but when you think you have a problem and you have something, go ahead, hook up a profiler, and then measure that you actually fixed it. You have to tune and then verify. All right, let's talk about optimizing for reads. So remember, this is how CQRS works. A command comes in for the user, something like register user. It's dispatched to our handler. The handler actually raises an event that says the user was registered back to the event bus. Our event handlers pick those up, and they respond to that. They then write the data to storage, and those are more or less directly returned to the user. That's read optimization. So, first tenet, pre-calculate and store any view that you think you're going to need in the system. So if you have a screen and the user's inputting data or looking at their profile or trying to look up parts or whatever it is, create a view for that. Storage is cheap. It's okay to duplicate the data. Just because you have the same data in one view as the next view doesn't matter. Storage is very cheap. Don't make your web roles work hard. Okay? You don't want them querying and joining and putting things in memory. This is the piece that's going to get seen by your users. Right? The back end that's asynchronous, it can actually be slow. It's hidden from the users in most cases. You can have bottlenecks in there that can be relatively hidden until you fix them. But the UI, the user's going to notice right away if it's slow. When you cache and use e-tags on things like JSON files, you can even further optimize because the customer won't even ask for you to send the file again if you send them an e-tag that says, hey, you have the latest already. Now, one thing that really bothered me when I first started with CQRS was, I was like, but everything's stale, right? It takes a while to go around. It could be 1 second, 2 seconds, it could be 2 minutes, who knows? It really, really bothered me. And then I learned to live with it. You'll get there too if you use this pattern. But everything by definition is stale in this world when you have a view. The user could, even if you have a live system and you're querying live data, the second the user makes that query and sits on the screen, they wait 10 seconds, that data is 10 seconds old. They'd have to hit F5 constantly in order to keep it up, right? It's okay if the data is stale. When you create a view for each task on your UI, there's going to be two general types of data that you have. I term it static and dynamic. Okay? And here's what we did. For dynamic view data, this is essentially our queryable data. We actually use table storage. Turns out table storage is perfect for this. So imagine, if you will, in our scenario, the user wants to know what their last 2 hours of traces are that have a warning or higher. It's a very reasonable query. We looked at that and we said, well, how can we structure a view that works out? We created a special table for that tenant, for that tenant's deployment. So it was unique to that tenant's deployment. Inside of there, we reverse sorted by date time, and then we used the level, the trace level, as an index on the row key. So all our web server had to do was say, return to me something less than greater than this partition key range, where row key greater than equal to this trace level. It didn't do any work. It just took the data, just basically threw it right back to the client. All of the querying, so to say, was pushed to the table storage. Our UI had to do basically nothing. For our static data, so this is like, what's the state of your scheduled task? What's your secret key? What's your name? How many deployments do you have? What's the current name of the deployment? Where are they located? What should your dashboard look like? In our world, this is just static data. It gets updated every 5 minutes. This is ideal for the JSON file sitting in Windows Azure Blob Storage. Just serialize it into JSON, stick it into Blob Storage. Customer goes to ask for it, you find the file, send it back to them. Use something like Knockout. We use Knockout. You can use Ember.js. You just bind this JSON directly to your HTML. Works fantastic. Combine it with e-tags, even better. One of our next tenants, work close to your data. I know it sounds crazy, but the bandwidth actually becomes a limiting factor in a lot of cases for high-scale systems. So it's bandwidth between data centers and bandwidth between the machine and the storage. When you move close to the data, your cost actually goes down, right? Bandwidth is free within the data center. So your cost goes down and your performance goes way up. It's like a win-win. That never happens. Usually you got to pick one. In order to do that, though, to work close to your data, A, you're going to have to be deployed in multiple data centers, and B, you're going to have some strategy to route to those data centers. In the CQRS world, that's really easy for us, because we could take a look at a command coming in and say, who is this destined for? Oh, it's for somebody in North Europe. Push that message out to North Europe and let the resources working in North Europe do it, right? So we could deploy and dispatch because we had a message routing strategy. This also ensured that our messages got prioritized, and if we saw the same message showing up multiple times, it could actually be quarantined and get it out of the system so it quit clogging up the pipes, so to speak. All right, so we talked a lot here. These are the main points again. We have read optimization, work close to your data, right? Got to push all your hard work to the queues. Got to learn to live with stale data, instrument, and optimize for reads. Now I'm going to have Wade come up and give you a demonstration, because next we're going to be talking a little bit about how we built our automation at Aditi. There you go.
Great, thanks. So one of the things Ryan mentioned earlier is that we don't have a very large team, and one of the ways to compensate for that is to really start to find more efficient ways of leveraging your teammates. And in many cases, when you have a team size of 4 or 5, you don't have someone that's just dedicated to your builds. And so one of the areas that we found huge efficiencies was in really automating all the processes, all of our builds, continuous integration, running through our tests and so forth. And so what we thought is we would talk a little bit about this and actually demonstrate some of the tools and some of the ways that we do this and actually kind of prove that this stuff really works pretty effectively. Now, one of the things to mention is that in our world at least, we have a rule, and that is that deploying, especially to production from Visual Studio, is completely forbidden. Even in development time and in our dev test environments, we don't want to use Visual Studio as a deployment tool because it becomes very difficult for us to reproduce behaviors when you're counting on how someone has configured their settings within Visual Studio and started doing those deployments. So we love Visual Studio. We love the tools. And as Ryan said, used to evangelize them. But it does turn out that there's a cost when you become dependent on those tools as well, especially for smaller teams, and you're looking to automate and reproduce a lot of this. And the other thing about automating your builds in these environments is it does take the I forgot out of the equation. If you think about scenarios like Ryan mentioned, when you're deploying services into 6 different data centers worldwide, you're going to have different connection strings. You're going to have different passwords. You're going to have different DNS names, and so on and so forth. And the ability for someone to forget or make mistakes when it comes to all these different configurable settings is pretty high. And things will happen, and people will make mistakes. And so by automating and having these continuous builds and these methods for deploying, it not only raises the bar, but it also makes things a lot easier. Now, one other point here to mention, and we're not going to necessarily demonstrate this today, but is data migrations. As you think about it, over time, your schema and your views and these things will evolve. And so as part of this automation, you have to also take into consideration how are you also going to be migrating your data from one type of view or one schema into another. Ryan mentioned that in our world we use events, and so we have the ability to replay these events and to create different aggregates and different views. But in your world, you may use relational database, you may use Entity Framework, and some of these tools help quite a bit. But if you don't use things like Entity Framework, then you may need to find other ways to do it as well. But actually being able to automate your data migrations is a very important part. So what I'm going to do is flip over and demonstrate a little bit of this. So we use a tool called TeamCity. Does anyone here use TeamCity? Familiar with it? Good, excellent. There's a lot of tools out there you can use. TeamCity is a really good one. And what I want to demonstrate is some of the ways in which we've configured our environment so that it becomes really easy for all of our developers to be able to leverage this automation and have this reproducibility. So essentially what we have here is our super secret build server. This is actually our production build server. We didn't want to take the time to set up a separate one, so we just created a DNS name to mask what our actual build server is. But for all intents and purposes, this is our super secret build server. And we do use this for all of our services today. In fact, for our scheduling service, we do have a scheduler project. And I'll talk a little bit about how we have this configured. So we have a couple of different concepts in here. You'll see that we've got the ability to push to production, dev test, and then we also have CI, or continuous integration builds. And we use these at different times. So for instance, for CI, as the name would suggest, every time we do a commit into our repository of any sort of source control changes, it will actually invoke a build within our system. And it'll run through unit tests and so forth. And I'll show you how we have that set up. But we also have a dev test environment, and we want to make sure that we can push these changes when we need to into our dev test environment so that we can test the integrations from different developers. We can make sure that we can publish. We can make sure that we can migrate data, so on and so forth. And then finally, the most important is production. And Ryan will yell at anyone on the team if they push any way other than going through our automation process here. Because we have checks, and we have the ability to control the action. So we can make sure that things pass all the tests that get run and so on and so forth. So these are the different types of projects we have for one of our services. So what I'm going to do is just demonstrate how this works pretty well. I'm going to come in here to our CI and show you how pretty easily any change that we make will end up getting picked up and then actually run through unit tests and so on and so forth. So what I have here is just here's our project, right? And I'm going to go ahead and create a new file, and I'll just call it temp file. And what it's going to do is it's going to create a new file. So it's now actually here in our directory, and so it's a new file that when I check this in, it will end up kicking off a build. Now, typically, we're not creating blank files. This would have code. It would end up being integrated in part of our solution. But this is just for demonstration purposes. So once I end up, I'll go ahead and add this to our repository. I'll commit it, test file for CI build. and then I'll go ahead and push it. And so this is going to end up pushing this change into our repository. And anytime this happens, we want to make sure that our build is actually invoked and it runs through all our unit tests. So if I come back here, eventually, now this will eventually refresh itself, but all I'm going to do is force it to check for pending changes. Any moment here, it should end up seeing it. But it'll find a pending change. You can see now it found one change. And in a moment, it's going to take an available agent. And since it's a change that needs to kick off a build and run through our unit tests, you can see now it has actually updated the current status. You can see that it is running. And so what it's doing is it's running through a set of prearranged tasks that we have here that not only grabs all the latest source, but invokes the build and then runs through our unit tests. And so when this completes, it'll either pass or it won't pass. And so this is a great way of, continually, enforcing some level of quality control, making sure that your unit tests are always passing whenever source control changes. And I'll show you real quick, too, here in configuration settings, the way we have this set up. So we have a couple of build steps. The first build step just uses MS build, and it'll grab everything and perform a build. Just make sure that it can compile, which is an important step in and of itself. And then the last thing is we'll use NUnit, and we'll just run through all of our tests in the test assembly. And we take the outputs and we use those as gate checks. Now this is just a continuous integration. If I come back to our projects, we'll take a look at production real quick. Production's got a few additional steps. If we look at build steps here, it does some similar things. It performs a build. We run through our unit tests, but then we also leverage PowerShell. And what's happening here now is we're using the Windows Azure PowerShell commandlets now to take the output of our build and deploy it into our production environments. And so we're able to configure for every environment and every data center, for every different configuration, these things in advance so that as part of now the process here, we can automate the full deployment of our services and our environments into a production environment. And this takes all the guesswork out of it. It makes it very easy for us to scale. We have the ability to move to different data centers if we need to. Let's say there's some problems in North Central or there's a problem somewhere else. It makes it very easy for us to move to a different data center. And to be honest, having this level of automation really makes it even easier for us to move into a completely different platform if we needed to. So theoretically, we haven't had to do this, but if we needed to move, let's say, into a different cloud platform, we could do so pretty quickly given the level of automation here. So just a couple of quick things for us to demonstrate and just show you some of the powers and capabilities here. So let me go ahead and flip back. And so here's our demo. And just as a real quick recap, I mean, especially when you have a small dev team, without having the ability to automate these sort of capabilities, it becomes extremely difficult to stay agile, stay nimble. Having this level of automation really takes a lot of the guesswork out and reduces a lot of the pain points and problems. So with that, I will turn it back to Ryan.
All right, so we talked already about kind of the lessons we learned building for scale. We talked a little bit of how we run our automation and how we actually build our environments. And now I want to focus on a little bit of how we chose our deployments. Some of this is going to be controversial. Mark Rosinovich might punch me in the neck later. But we'll talk about it in the context of what we found in practice, right? So for large-scale deployments, right, if you need to go over 50 instances, already you're on PaaS. Currently, the limit in IaaS is going to be 50 instances. And same with Windows Azure websites if it was relevant to this discussion. It turns out the PaaS model is actually much, much easier for deployments, updates, upgrades, so on and so forth. You're kind of on your own on IaaS. It's not impossible, but you're on your own. IaaS itself is fantastic for stateful apps. That's what we use for our build servers. Really good for build servers. Not so hot when you want to spin up, potentially peak at 50 to 60 workers trying to aggregate data. It doesn't work real well in that case. So what we say is PaaS for the win, for right now at least. Okay? Now IaaS, I'm sure they're going to continue to improve it, and some other capabilities will come out there to make it more PaaS-like. And when that happens, this opinion might change. But for now, if you're going to build large-scale services, and especially anything like what we're building at Aditi, PaaS is our much preferred model over IaaS every time. The only exception, again, is our stateful services. So if we were running a SQL server in the cloud, or if we're running a build server, then IaaS makes total sense. Extra small VMs. These are really a hidden gem. How many of you have used extra small VMs? A few of you. You guys use it just for testing, or do you actually use it in production? Shaking heads, not production, not production. Look, if you can live within the memory constraint, usually that's the first one, these are awesome bang for your buck, right? You can get them doing all sorts of stuff, running scheduled tasks, waiting on long IOs, looking at queues, routing, and they're like, right now, they're 4 times as cheap as a small. So you can get a lot of bang for your buck on these. They're not just for dev test or really small websites. We used 12 of them, and they were key in our environment. We'll talk a little bit here about websites versus web roles. So up front, the Git deployment for Azure websites, really great. Love it. But the ability to use the role entry point, actually, on a web role, for us, completely outweighs any of the benefits in an Azure website. So we want our instances to do more than just IaaS usually, or IIS, I should say. We don't want it just serving web pages. We might actually be running other agents on there, and in our case, we might be running that framework that actually does message dispatching. So we're going to take full advantage of the web role. It also means we can load custom components on there, and we can configure it exactly how we want. And I don't know if you heard, but SSL is free in the PaaS model. You're going to have to pony up if you want to use Azure websites right in the current model. So again, we say for high-scale applications especially, it's web roles for the win. Single versus multi-deployments. So when we were first starting Windows Azure, do you guys remember everybody said, you got a service definition, you put all your stuff in the service definition, you deploy it as one big unit. There were some really good benefits to that. You got same, network connectivity. It was the only way if you had to have internal endpoints at the time. It was really good for upgrading certain roles and keeping all of your assets together. Well, it turns out most of the time in large-scale applications, you're going to be multi-data centers anyways. So you might as well start splitting up your deployments. We actually split completely our web front ends from our back ends. We version those. We use them completely separately. Remember, our model is we serve basically static files off of disk. There's nothing it has to integrate with. It needs a JSON serializer. That's it. I share a contract at the end of the day that says the view looks like this. Here's how I should serialize that JSON. That's it. I don't have any other dependencies on the rest of the system. So I can deploy that anywhere. When we add in the ability to dynamically route our messages, we actually have a pretty neat capability in here. So if a data center is having issues, we can actually turn the routing off and move the messages for that work to be put to a different data center. Okay? When it stops having issues, we can then adjust the routes again and have the messages go towards the affected data center. During an upgrade, we can actually stop all traffic going into that data center for work. We could get the upgrade done, and then turn the routing back on, and then it starts responding. We've used this to our advantage many times. Okay, so again, the PaaS versus IaaS, we lean towards the PaaS. Websites versus Azure, web roles versus websites, we're going to go web roles. Single versus multi-deployments, there's something you should think about at least. And then finally, extra small VMs. If you're not using them, really anywhere you see the small VM, take a look at it again real closely and see if you can get an extra small working on there. You get a lot more bang for your buck. Throw up multiple instances, right? Now we're going to talk a little bit about handling disasters and outages. So it turns out when you write a monitoring solution for Windows Azure that monitors other people's deployments in Windows Azure, you see a lot of outages. Like the dashboard doesn't even reflect a fraction of the actual outages. Now it might not be data center wide, but it could be, just happens to be the stamp or the cluster that you're located in for maybe 5 minutes, 10 minutes, but you're completely unreachable for that period of time. We saw that a lot. I can't emphasize that. The outages are extremely common. And I don't think it's a case of Windows Azure is bad or they did something wrong. I think this is true anywhere in the cloud. Now, data center level outages are relatively rare. Within the chance of your particular storage account, service bus, SQL Azure, or compute having an issue, pretty good. You're going to have one once a week probably. You don't even notice it. Might be for a couple minutes, but you'll have it. It will happen. Thing to keep in mind here is every service has its SLA. I think there was a lot of confusion. Say, well, you have 99.95% availability if you deploy at least 2 instances. Yes, for compute. But then when you added SQL Azure into it, and then you added storage into it, and then you added the service bus into it, and so on and so forth, it's actually multiplicative, right? At the end of the day, just having 3 different services, you can get down to 99.75, which is not what you probably thought it was. So you will go down at some point. So this is the part where I stand here and say, I feel like a drug commercial, right? And they say, well, every user will be different. Some people may get hot dog fingers, and other people may have swelling of the eyes, and other people may choke. And this is to some extent true in this world too. It's going to be very dependent on your application, how you choose to handle it. You got to weigh your risks here. Should you go multi-cloud, multi-data center? Don't worry about it. Have an hour outage, big deal. For us and Aditi, we took a look at how our infrastructure was set up, and we found that we had really one big single point of failure. And that was if storage went down. If storage absolutely died, we were dead. Okay? We also found building a monitoring solution in Windows Azure to monitor Windows Azure might not have been the best choice. Because if Windows Azure is dead, your monitoring solution is dead. Right? So we had to think about these things. And the next version of we have internal monitoring tools now. Those are actually running in Amazon now. And they monitor our Azure assets. Because we don't want Windows Azure going down to affect the monitoring of the rest of our system. Like if we don't get notified that our stuff is down because our notification is down, that's a pretty big problem. All right. We also found, though, that because the way our architecture was set up, and we were queuing all this work, you guys remember the big outage that happened like last year? It was like leap day certificates, all that kind of fun stuff. Okay, we queued a ton of work. Our system was unable to scale because service management wasn't working. We had all sorts of problems. But as soon as it started working again, our autoscaler went crazy, kicked up 30 instances. We just pounded through those queues in a few minutes, and we were back running normally. And we were able to completely recover. And it was because we were using queues. The last part here on geo-distribution. So again, depending on the type of app that you have, you might want to be in different data centers. You might want to be in different clouds. For a monitoring solution, we definitely want to be in a different cloud. If we're building, and we have been working on some solutions that are for emergency management notification, right? We can never be down. You're going to want to deploy to multiple clouds. But for our scheduling solution, if it goes down for an hour, that's okay. We're willing to live with that risk right now. Right? We might have a few unhappy customers that their job should have executed, but we'll be okay with that. We'll give them their money back or something like that. But we'll be okay. the end of the day, the 4 points that we want to talk here are what we learned around building for scale, how we handled our risks, our trade-offs. It'll be different for you guys probably. What we really did and what we thought about for our deployments and how that worked for us. And finally, talk a little bit about how we did our automation and how we were successful with our teams, our very small teams, building out very large solutions within Windows Azure. With that, I want to remind everyone to do their evaluations. They told me I had to say this. So don't forget to send in your evaluations. And I think I have a few minutes left. How are we doing on time? I have about a few minutes left to actually take questions. Anybody have any about any of the things we've covered here? Yes? Okay. So the question is, how do we handle changes to production where the data schema changes between... okay. So in our case, we had what were called data migrations that actually handled that for us. During a deployment, what would happen is if we had a known schema breaking change, what we did was we created something called an upgrading serializer. So the upgrading serializer knew how to handle the old event plus the new event. And as it got deployed and rolled to the clusters, what would usually happen is we couldn't stop a few of the old instances from hearing the new events, but that what they would do is they would just throw them away instantly. They didn't understand. They'd throw them back into the dispatcher. Our new instances, as they rolled up, they would get the new event. They knew how to handle it. They would use that upgrading serializer to handle both the new event and any of the old events that might still be in the queues, and they would take over. And then eventually the old ones would get rolled out, and everything was new, and at that point it just worked. At the same time, if we had to build our views, we would build our views right there. Yeah, as the role booted, if we knew there was a view change, we actually had what was called a migration script that would kick off automatically. And what it did was it would replay all the events and build the new view. Yeah. But most of the time, actually, it wasn't the views that we were worried about, it was the events. So the events, if they got upgraded and we had a new field or we changed the type or whatever it was, those were the ones we would have to actually be concerned about. Any other questions? How many of you have deployed to Windows Azure something you would consider a production app, not test? Half the room. That's really good. How many of you have looked at this and said, we do this today? One. It's late today. I'm keeping you guys from lunch, right? All right. So in the world that we're talking about here, where we've split our reads and writes, we have a lot of flexibility. I do want to point out there was one downside. The downside that we really have in this model was because the reads and writes are split, there's this asynchronous behavior where the client doesn't get the data instantaneously, which for a web client is problematic because you're going to have to do something to tell the client that it's in process. What we ended up doing was throwing the little spinning GIF, up on the screen, and then looking for that view to see if when the E tag changes, we know it was updated. In our newer solution, we actually went a little step further. As we process the command, we write the status of the command into another table. And then the client actually queries the table, says, I just told you to update this, and here's the ID for that command. Tell me what the status of this command is. We say it's pending, it's processing, and then if it failed for some reason, we actually tell them it failed, and we'll return the error information. So then the user can actually see the reason why it failed right in the UI. SignalR for the future, perhaps. I'll admit, SignalR has been on the top of our list to investigate. The reason we don't currently use it now is because I'm not quite sure how to... Remember, our worker roles are completely way over in another data center, processing all this stuff. Our web roles are not the things doing the work. So if they're attached to that role, I don't know how to then attach them to the thing that's doing the work to tell them it's done. So we have that additional hop. I'm sure there's a way, and if someone's really good as signaler, they can set me straight, but at this point, we're using a table to intermediate, right? How often, the question was, how often does the client query the table to see the status change? In our model, it queries every 5 seconds. But that's not a constant thing, right? It only does that querying after it sends a command. So it's not like it just sits there and pings every 5 seconds. It knows that it sent a command in, and now it just needs to check on the status of it. Yeah. All right. If there's no other questions, we'll be here for a few minutes upstage, but I want to let you guys get a chance to go to lunch. And thank you for letting us speak to you today. Have a great rest of your TechEd. I appreciate it. Thank you.